By shining white light on a glass slide stippled with millions of tiny titanium dioxide pillars, researchers at the National Institute of Standards and Technology (NIST) and their collaborators have reproduced with astonishing fidelity the luminous hues and subtle shadings of Girl with a Pearl Earring, Dutch artist Johannes Vermeer's masterpiece. The approach has potential applications in improving optical communications and making currency harder to counterfeit. For example, by adding or dropping a particular color or wavelength of light traveling in an optical fiber, scientists can control the amount of information carried by the fiber. By altering the intensity, researchers can maintain the brightness of the light signal as it travels long distances in the fiber. The approach might also be used to paint paper money with the small but intricate color details that a counterfeiter would have great difficulty forging. Other scientists have previously used tiny pillars or nanopillars of varying sizes to trap and emit specific colors when illuminated with white light. The width of the nanopillars, which are about 600 nanometers in height or less than 1/100th the diameter of a human hair, determines the specific color of light that a pillar traps and emits. For a demanding test of such a technique, researchers examined how well the nanopillars reproduce the colors of a familiar painting such as the Vermeer. Although several teams of researchers had successfully arranged millions of nanopillars whose sizes were tailored to transmit red, green or blue light to create a specific palette of output colors, the scientists had no way to control the intensity of those colors. The intensity or brightness of colors determines an image's light and shadow and enhances the ability to convey impressions of perspective and depth, a signature feature of Vermeer's work. Now, by fabricating nanopillars that not only trap and emit specific colors of light, but also change its polarization by varying degrees, the NIST researchers and their collaborators from Nanjing University in China have for the first time demonstrated a way to control both color and intensity. The researchers described their findings in the journal Optica. In their new work, the NIST team fabricated on a glass slide nanopillars of titanium dioxide that had an elliptical cross-section rather than a circular one. Circular objects have a single uniform diameter, but elliptical objects have a long axis and a short axis. The researchers designed the nanopillars so that at different locations their long axis was more aligned or less aligned with the polarization of the incoming white light. Polarized light is light whose electric field vibrates in a particular direction as it journeys across space. If the nanopillar's long axis was exactly aligned with the direction of polarization of the incoming light, the polarization of the transmitted light was unaffected. But if the long axis was rotated by some angle, for instance 20 degrees, relative to the direction of polarization of the incoming light, the nanopillar rotated the polarization of the incident light by twice that angle, in this case 40 degrees. At each location on the glass slide, the orientation of a nanopillar rotated the polarization of the red, green or blue light it transmitted by a specific amount. By itself, the rotation imparted by each nanopillar would not in any way alter the intensity of the transmitted light. But in tandem with a special polarizing filter placed on the back of the glass slide, the team achieved that goal. The filter was oriented so that it prevented any light that had retained its original polarization from passing through. Sunglasses work in much the same way. The lenses act as vertically polarized filters, reducing the intensity of horizontally polarized glare. That would be the case for any place on the glass slide where a nanopillar had left unaltered the polarization of the incident light. Such a region would project as a dark spot on a distant screen. In places where a nanopillar had rotated the polarization of the incident white light, the filter permitted a certain amount of the red, green or blue light to pass. The amount depended on the rotation angle. The greater the angle, the greater the intensity of the transmitted light. In this way, the team for the first time controlled both color and brightness. Once the NIST researchers had demonstrated the basic design, they created a digital copy of a miniature version of the Vermeer painting, about 1 millimeter long. They then used the digital information to guide the fabrication of a matrix of millions of nanopillars. The researchers represented the color and intensity of each picture element or pixel of the Vermeer by a group of 5 nanopillars, 1 red, 2 green and 2 blue, oriented at specific angles to the incoming light. Examining the millimeter size image that the team had created by shining white light through the nanopillars, the researchers found that they reproduced the girl with the pearl earring with extreme clarity, even capturing the texture of oil paint on canvas. To construct the nanopillars, the research team first deposited a layer of an ultra-thin polymer on glass, just a few hundred nanometers thick. Using an electron beam like a miniature drill, they then excavated an array of millions of tiny holes of varying dimensions and orientations in the polymer. Then, using a technique known as atomic layer deposition, they backfilled these holes with titanium dioxide. Finally, the team etched away all of the polymer surrounding the holes, leaving behind millions of tiny pillars of titanium dioxide. The dimension and orientation of each nanopillar represented, respectively, the hue and brightness of the final millimeter size image. The nanopillar technique can easily be adapted to transmit specific colors of light with particular intensities, to communicate information through an optical fiber, or to imprint a valuable item with a miniature multi-hued identification mark that would be hard to replicate.